Hello, everyone. It's time to start. So my name is Chunmei from Intel. And this session, I will introduce the implementation of persistent red log cache with replication in Ceph. So in this session, there's two main parts. We have implemented the local persistent memory cache and the remote replicated persistent memory cache. So I will introduce the two implementation. So let's see the general workload in the Ceph cluster. On the left side, there's a normal I/O request path. In the computer node, there is applications such as the QEMU and other applications use the disk. Then the disk L will transfer to the Ceph backend storage node through the TCP/IP network. And the Ceph storage node will handle the I/O request and write the data to the backend storage, such as hard disk SSD, NVMe SSD, such as that storage device. In the left normal I/O path, the application write directed to the storage node. The burst write will increase the backend pressure, will cause the bad latency for the I/O request. So there is an improvement for the I/O request. The Ceph community add the RBD cache in the client side. So the data write to the RBD cache first, then write back data to the Ceph cluster. But this RBD cache is memory cache, so there is a risk of data lost. So in our team, we implemented the persistent memory red log cache. The persistent memory red log cache replaced the RBD cache in the RBD client side. You can see the right frame in the RBD. So this is the Ceph cluster, storage cluster architecture. And we only replace the RBD cache by our persistent red log cache. We can call it a PWL cache in short. And the goal is that to improve the Ceph RBD write performance and mask reduce tail latency, keep 99.99% of user request tail latency within 1 millisecond. So guarantee the write durability through any single failure compared with RBD cache because it is persistent memory. And when you write data to the persistent memory, it persisted. For the user case, this scenario is worked for the workload required for low latency. Average latency and the tail latency has the high requirement for the latency, such as database and QEMU, and need a persistent feature as high performance. We have implemented the two kinds of the persistent cache, red log cache. One is used persistent memory, another used NVMe SSD. In this session, we only introduced the PMEM mode. So in the PMEM mode, we have the local mode and the replicated mode. For the local mode, just mean that the data just write to the client local or PMEM device. For the replicated mode, we have the replicator, and you can write several copies to other node to do the replicator. So now let's introduce the local persistent memory mode. So this hierarchy is the memory storage hierarchy. From the top to on the right side is the latency. From top and to the bottom, the latency is increased. And the left side is the price, the capacity. From the bottom to the top, it is reduced. The cost is increased, but the capacity is reduced. So the persistent memory is in the middle. It offers greater capacity than DRAM and significantly faster performance than storage. So it is cheaper in DRAM, but more faster than SSD. It also provided the persistent feature. Application can access the persistent memory resident data structures in place. That means the persistent memory, you can access it in bytes, address it in bytes. Like you do with the traditional memory, you can use the semantic instruction like the local DRAM memory. Just use the load store semantics to access the persistent memory. And you needn't use the DRAM to do the page cache of the data. So the persistent memory also can be accessed directly by RDMA method. And in our implementation, we use the PMDK, the lab PMEM library, to use the persistent memory through the lab PMEM library to code, to write to, and manage the persistent memory. So the bottom chart shows you have two methods, two ways to access the PMEM device. One is just like the local DRAM memory. You can use the same semantics, load, store, and MMU mapping. Another is use the native file system API interface, but it means the file system need aware the PMEM exists. So for the local PMEM cache, we have the layout on the PMEM cache file. So for each cache, there are the cache file created in the PMEM device. And for each cache file, we have the same layout. The layout includes three parts. The first is the super block. Second is the cache entries. And the last one is the data area. For the super block, we have two copies. Not copies, it's just a round robin to access the super block. For the even write, we write to the first super block 0. For the odd write, we write to the super block 1. So it's depending on the write number. And in the super block, we record the log entries number, how many cache entries in this cache file. And two pointers. One is the first free entry pointer, another is the first valid entry pointer. The valid entry pointer means that there is data have written to the cache entry. And free means that empty, you can use it. So that is the super block information. And for the entries, that is there are several cache entries in the entries part. And each entries will save the following information: the offset in the image, the data length, the offset in cache. The offset in cache means where you save the data in the cache file. And the offset in image, that means the logical address in the RBD image. And the data length recorded how long the data is. So the cache entry is a ring composed of log entry pointer to the allocated data buffer. And in order to guarantee the right order sequence, when the client issues the flash command, we put empty or a special point cache entry into the entry. Means that when the background thread write data to the Ceph cluster, before the sync point, the catch entry you can write together. But after the sync point, you have to wait until the catch entry before the sync point finished. So that means we not mask the data content. So here is the persistent write log catch write operation flow. So our code is plugged into the RBD, lab RBD. And when the lab RBD issues the IO request, and the IO request goes to the PWL layer, the PWL will check if there's the resource in the catch file. If there is free resource in the catch file, if there is the resource, and it will reserve the results for this IO request. If no resource, it will put the IO request into the left side defer queue. So then if there is a resource and we reserve the results, means the reserve the catch entry and reserve the data buffer in the data part, and we'll write the data, the user data to the data buffer, to the data parts, and flush data to persist memory. When you write it and flush it, it persisted. Then write and flush the catch entry, the entry information into the catch entry. At the end, to update the super block to modify the free tail pointer and the first available pointer. So we pointed that the catch is a ring. So when there is the dirty catch entry, it means that when there's user data write to the catch, we mark it dirty. And the background, there's the background thread. When check there is a dirty catch entry, the background thread will write data back to the Ceph cluster. The Ceph cluster then write the data to the SSD or hard disk. So once there is a dirty catch, the background thread will work. So when the background thread write the catch data back to the Ceph cluster, it will mark the catch entry clean, but it is still valid. So when you read the data, the PWL will first search the PMEM cache. If there are data in the PMEM cache, it will return from locally. So it make it mark it clean means the data still available. When the clean entry and the dirty entry added together is bigger than threshold, is the number we set, and we return the cache entry. Return the cache entry means that the cache entry is freed and you can use it again. The data is not available. So in the local, all the cache entry is used locally, and background thread will write data to the backend Ceph cluster. And the local read-write first write to the cache and first read from the cache. So that is the local persistent memory cache. And next, I will introduce the remote replicated implementation. So for the remote replica, we use the RDMA to from the primary client right to the replicator. The RDMA enabling a user-level program to directly access the memory of another computer without interrupting the processors. In our implementation, there are two ways. One is the control flow, is the upper dash line. That means the target node CPU will be involved. The target node CPU will aware there is the message sender. And another way is the data flow, is the write solid line. The data flow is offloaded from the CPU. The target node CPU will not aware there is the data right to come in. So RDMA, there is two working mode. One is the one-sided primitives. We can use the read-write instructions to do the data read-write. RDMA capable NIC can directly read-write the server memory by passing the server CPU. That is the write solid line means the one-sided primitive. And we used the lab RPMA to do the RDMA transfer. And the second mode is two-sided primitive. We use the send receive instruction as similar as the TCP/IP message parsing. So that is the dash line upper in the top is the control flow. Control flow, so it's the two-sided primitive. The target node the CPU will be involved in. How to direct write to the persistent memory on the target node? So in order to enable direct write to persistent memory, you have to turn off the inter-direct data I/O, means DDL, direct data I/O, on the target node. So direct data I/O, if you enable it, the RDMA write may be write to the processor cache. So we disable it, turn it off, then the RDMA write will write to the PMEM directly. Will not write to the processor cache. And we use the lab RPMA, this library, to accessing the remote persistent memory and execute the remote direct memory access. There's two steps to write to the remote replicated. The first is you issue a RDMA write that we call the RPMA write function. Then the data will write to the target node PCIe device, but it is not write to the PMEM currently. Then the following, we issue the one RPMA flash. The flash is a read operation, and that is the purple one. Yeah. So this flash will trigger the PCIe device write the data to the PMEM. So finally, the transfer to data to the remote memory. The two-step issue the RPMA write data to the target PCIe device, then issue the RPMA flash. The data will automatically from the PCIe transfer to the persistent memory. Let's see how the replica work. So this is the overview. There are three roles in the replica PWL mode. The first is the client memory. The memory client. The memory client has the local PWL. And we want to guarantee there's no single point of failure. We have to copy the data into mirrors. So we can assign some replica for this primary. And from the client, primary client and the replica, they use the RDMA lab RPMA to do the data write and control. And there the Ceph cluster is the backend Ceph cluster storage. All the data will write to the Ceph cluster, then Ceph cluster write to the backend SSD or HDD. So The replica service running in the replica is a daemon process, and the replica service manager in the Ceph cluster, running in the Ceph cluster, it is used to manage replica service in Ceph cluster. And when the primary alive, the background thread will write to the data to the Ceph cluster once the cache entry is getting dirty. If the primary client died or something happened not connected, and the replica will write the data to the Ceph cluster. So that's guaranteed the data will not be lost and consistency. In the Ceph cluster replica management, there are several important data structures. The first one is the replica daemon information. That is, the replica tell the Ceph cluster his self information, and Ceph cluster use the replica daemon info to manage the replica. Another one is the uncommitted caches info. When the client, primary client, asks the Ceph cluster to assign the replica, Ceph cluster will create this data structure to record the cache size, copies, and cache ID and the replica ID. Means Ceph cluster assign which replica to be the client primary's replicator. And when the client succeeds to connect the replicated daemon, it will tell the Ceph cluster, we have finished, we have set up the connection. And the Ceph cluster will transfer the uncommitted cache info to the committed cache info. If the client, the primary client failed to connect it to the replicated daemon, or client occurs error, which leads to expired or RDMA disconnected, the committed caches info will convert it to need to free daemon space caches. So that is one data structure change his status during the different cluster states. In the replicated PWL mode, there are several kind of control process. So the first one is when replica daemon startup, it reported to the Ceph cluster its self information such as RDMA IP, RDMA port, and totally size such as that information to tell the Ceph cluster. It's the first kind of control. Another one is the second one is that the client requests the replicated daemon's information from the Ceph cluster. The third one, the Ceph cluster reply replicated daemon's information to the client, or there's no space. The fourth control is that the client connects to the replicated daemon to ask the replica to allocate the cache space for the primary client. The five control is that the client acknowledge this connection success or failure to the Ceph cluster. That means the client tell the Ceph cluster, the replica, we have a set up connection with the replica, and the replica has already allocated the space for me. So the Ceph cluster will convert the uncommitted cache info to the committed cache info. And the sixth control is that when the client primary application shut down or finish work, it will free the caches from the replica. So it will tell the replica to free the cache you allocated for me. The seventh control is that the heartbeat between the Ceph cluster and the replica. So the replica used the heartbeat to make Ceph cluster know the replicated daemon status, and the Ceph cluster will return the replica if you need some cache information. The eighth control is that the client set up the heartbeat with the Ceph cluster to tell the Ceph cluster the client status. So let's introduce each control one by one in detail. When replica daemon start up, it reported to Ceph cluster information, the replica daemon information, the ID, client ID, the replica's client ID, and the RDMA IP, RDMA port, total size. The first, at the beginning, free size equal to the total size. When the Ceph cluster allocates the cache, it will reduce the size from the free size. And expiration, because there is the heartbeat between the replica and the Ceph cluster, expiration will be updated once they receive the heartbeat. At the beginning, the need-free cache is empty when the replica start up. The second step is client request the replicated daemon information. The Ceph cluster will search the replica daemon info to check if the free size meet the client request. Client will tell the Ceph cluster how much size the cache is needed and how many copies. So Ceph cluster will search the replica daemon info, find out the available replica, and created the uncommitted cache info. So set up expiration and cache ID. Primary ID is the primary client ID, and recorded the cache set copies and put each replica's ID in this table. And return the RDMA IP and RDMA port to the client. So means that tell the client which replica you can use. And the client will connect to the replica use the IP and the port and tell the replica to allocate the cache size from replica's PMEM device. And once the connection set up and the replica reply to the primary, the client acknowledges this connection success or failure to the Ceph cluster to primary tell the Ceph cluster is the five steps. So if it is succeed to connect it, so Ceph cluster will convert the uncommitted cache info to the cache info that is committed, means that the cache allocated success. If it is failure, there is failure, and this uncommitted cache info will be converted to the needed to free daemon space caches. So to tell need a recorder this replica application, replica cache needed to be freed from these replicas sets. In this table, there are the replica daemon IDs. So next time, when the replica connect to the Ceph cluster will tell the replica you need to free the caches. So this table, uncommitted table, will be dropped and it converted to needed to free daemon space cache. So normally, it is primary client to tell the replica to free the cache space you allocated for me. But if client succeeded to free daemon space, then the Ceph cluster will drop the cache info table. If the client tell the replica not worked, means the connection not set up or some error happened, it will tell the Ceph cluster, I can't ask the replica free. You have to do that. So when the replica heartbeat with the Ceph cluster will tell the replica to free the caches you allocate for which primary client. So if it failed, the catch info table will convert to need to free daemon space catches. So Ceph cluster will convert this table to the original, not orange color table. So need to ask the replica to free it. The heartbeat between the replica and the Ceph cluster. So when the Ceph cluster get the replica heartbeat, it will update the expiration, set the next time to expired, and will check if need free the catches. There is a catch ID recorded in the need free catches. Through the catch ID, we can find the need to free daemon space catch info. Then find the delete replica ID from this replica ID list, and tell the replica you should free the catches in your PMEM. So if the replica set heartbeat failure, there is a failure, the Ceph cluster will drop the replica daemon information and search the catch info, find this replica daemon ID, then delete it. Means that this replica copy doesn't work. The last one is the primary heartbeat with the Ceph cluster. So when the Ceph cluster gets the primary client heartbeat, it will update the expiration. If the ping expired, the Ceph cluster will drop the catch info table and convert it into the need to free daemon space catches and record the catch ID to the replica daemon info. So then the Ceph cluster will tell the replica to free the catches. So before is the control path. Currently, we talk about the usage data, the user data path. So user data, we have discussed there are two ways. One is the control. For the control, use the send, receive, RPMA send, RPMA receive instructions to talk with the target node. For the data path, just use RPMA read and RPMA write to write the data to the replica. So the local PWL replica is the mirror of the local PWL, so they have the same copy of the data every time. So the replicated mirror IO process, when the IO request is dispatched to the PWL layer, it will check if there is the free resource. If no free resource, it will put the IO to the default queue. If there is a resource, free resource, include cache entry and the data space, if there is a resource, enough resource, it will reserve the resource, allocate the space. And PWL will write and flush the data to the persistent memory, to the local persistent memory, then write to remote persistent memory. Next step, PWL write and flush entry to the local persistent memory and to remote persistent memory. In the fourth step, it write the cache entry. Last, update the persistent super block on local persistent memory and to remote persistent memory. So the replica's cache is the same as the local persistent memory cache. It's the mirror. And this is the performance with the local and the remote PWL. So we test the performance when the cache is full state. If the cache is not full, it is local write is more faster than write to the Ceph cluster. So we just test when the cache is full, how the performance influenced. And the left side is just the local mode performance. And the orange color is the PMEM cache. And the blue one is just write to the Ceph cluster, no cache. And the right side chart is with the replica. So it's with one replica or with two replica. So we can see that when the L depth is small, within 16, the local memory, local PMEM cache and the replica is faster than just write to the Ceph cluster. And with the replica is increased, with the L depth is increased. So the performance get a little worse with the local PMEM and the replica. So that its cache is full state we test. If it cache not full, it's several times or several tens times faster than write to the Ceph cluster. Okay, that's all. Thank you. So, any question? Mm-hmm. Yeah, so his question is that we have the local write flash sequence and the remote write local sequence. So we call the different library to the local write flash. It is lab PMEM, just you can use the PMEM, persistent memory as the memory, DRAM memory. And for the remote, we have use the lab, RDMA lab. So there's two write, two flash, you are right. Yeah, but the different library instructions call. Yeah, two write. Write local, write to remote, write flash local, flash remote.